Hey everyone, we're looking at the directions of magnetic forces on moving charges in magnetic fields, but this time we're making current loops in magnetic fields and trying to figure out how those forces work. So remember that the force on a current carrying wire is Fib, F-I-L cross B. Remember, IL is the current element, so we're going to put your fingers in the direction of the current, cross with the magnetic field, and figure out the force. So looking at the example we have here, the current is up, the magnetic field is to the right. Doing your right-hand rule, a magnetic force into the page on that wire. If you go across the top, the force equals 0 because the current and magnetic field are in the same direction. And then if you go down that wire, what you end up seeing is a I cross B, and you get a force coming out of the page. So technically, the net force on the wire here is 0. The force going into the page and the force coming out of the page are canceling out, so there is no net force on this loop. But if that loop is allowed to pivot, if it can pivot along this axis here, then the forces are acting a distance away from the pivot point. And when you have force acting at a distance, say radius r away from the pivot point, we now have torques, which means that that wire loop does feel no net force, but it does have a net torque, and the whole thing is going to rotate in this direction. Let's try one more example. So example 2 here, we've got the magnetic field coming out towards you and the current still going around in the clockwise direction. If you do your I cross B, what you end up getting is a force to the right on that first current loop. The second segment, it has current heading to the right, magnetic field out towards you. You now get a force down. And if you look on that bottom wire, put your fingers in the direction of current, curl out of the page, gives you a force in. So this one does have a net force, and the net force is inwards. So instead of making this wire rotate like the last example would, this wire would collapse in on itself. So current carrying wires in magnetic fields, if you make that wire into a loop, can create torques. And the torque, we can view that in two ways. One, we already drew the force in and out of the page to show you a rotation. But if we look at that wire from a side view, what we'd see from the side view is this. There is no net force, but down here at the bottom, I've turned the wire onto its side. So it's like taking the wire that was facing you and turning it 90 degrees onto its edge. So looking at that loop and tilting it, rotating it about 90 degrees in the plane here, you can see the current is going to flow around the loop in this direction. So if I look at an edge-on view, a side view of this setup, what I end up getting is current coming out towards me, so that would be a dot, current going along that front wire, and then that current going back into the page as it heads back. So the segment that I have drawn here is technically this segment right here, with the current coming out towards me, across the front, and then back into the page. The magnetic field here is going to be straight across. So the one thing I can tell you is that the force on this current in the magnetic field is going to be 100% 0. The current and the magnetic field are parallel to each other, so there's no force whatsoever. But that current that's coming out of the page on the right here is going to feel a force. So if you put your fingers in the direction of current, you curl in the magnetic field, you can see that there's a force up on this end of the wire. Do the same thing for the current going away from you. You're going to get a force down on this end of the wire. And if the wire is able to rotate, say the axis goes right through there, so the pivot is in this location, those forces are acting, like we said, a distance r away. So if I wanted to calculate the torque, we can calculate the torque like this. Torque equals r cross F, so r being the radius. In this case, I've got two torques. I've got a torque from the left and a torque from the right, and they're both torquing in the same direction. They're both trying to make the wire rotate the same way. So my torque equation is going to be 2 for both of those forces. The radius is going to be half the width, so I'm going to put the width of the wire divided by 2, multiplied by the force. Now the force on the wire is caused by Fib, so it's I-L cross B, or ILB sine of the angle between them. So the angle between the magnetic field and the current right now is 90 degrees, so you get maximum torque. But if you wait a few moments later. So if we wait until it gets to about a 90-degree rotation, you can see I still have my current coming out of the page and going back into the page. It's crossed with the magnetic field, but look at where your forces are. Take your current out and your magnetic field to the right, you get a magnetic force up on the top wire. And if you do the same thing for the bottom, you're going to get your current in, curl down, you're going to force down on the bottom part of the wire. But now the forces are in line with the axis. And if you're in line with the axis of rotation, right here, the torque equals 0. However, remember, you started off in line with the magnetic field. So you've actually rotated and accelerated from rest to this point. So yes, there's no torque on you, but you still have some motion. You're going to still have some rotational speed. So as you rotate through here, what you're going to get on the next segment. So again, I have an in and out of the page current here as I look at the currents and the magnetic fields. And if you look, I get a force down from the end of the page current and a force up from the out of the page current. And now they're acting at a distance from the pivot. Remember, the pivot's right through the middle here. I'm going to get a rotation again. But remember that we were already moving in this direction. So we already have an angular velocity in this direction, but now my torque is the other way. So if the torque is the other way, what it's going to do is slow down the loop. It's going to stop it when it gets to this 90-degree mark, and then it's going to try to accelerate it back. We'll be back to this scenario, but now we'll be moving in the opposite direction. And we'll fly right through that equilibrium point, and we'll head back to this location, where you have the current coming out on the right and in to the left, and that torque is going to slow it down. So we do have an issue when we have these loops. The loops are going to rotate, they're going to stop on the other side when they get 180 degrees across, and then they're going to rotate back. So you get a loop that's going to rotate back and forth. So if we look at our equation here, we've got the length of the wire, we've got the width of the wire. So if we go back to our equation and see if we can simplify things at all, we can get rid of the 2 here, and let's solve for the torque. Well, I've got width times length. That would be the area of our loop. So we can write our equation as area times current times B sine of theta. So this is how we can find the torque on a current carrying loop. I got to know how large the loop is, I got to know the current that's flowing through it, and I got to know the magnetic field strength. You get the most when they're at 90 degrees apart. So that means that technically I could write this as IA cross B, and that would be the torque for one loop. But if I wanted to get a stronger torque, I could increase the area, I could increase the current, or I could increase the magnetic field. But that's the torque on one loop. We could actually get torque by doing something very, very simple. Make this loop have multiple wrappings. So if I take and wrap up the wire into a current carrying loop, let's say I do it 10, 15, 20 times, all I have to do to find my new torque is multiply by the number of turns. So I could write NIA cross B would give me my torque on multiple loops in a magnetic field. And NIA we've called something special. We call that the magnetic dipole moment, or it's going to be written as little mu, not the coefficient of friction here, but the mu of the magnetic dipole moment. So there's a magnetic moment created by the number of turns, the current, and the area, and if you put that into a magnetic field, you can get a torque, as long as the magnetic field and the dipole moment are perpendicular to each other. So if you look at this one, if you see that current loop there, you can see I've got current heading in the counterclockwise direction. If I want to know the direction of the dipole moment, you can put your thumb in the direction of current and wrap your hand around, kind of like our first right hand rule for finding magnetic fields. So what we have here is a magnetic field pointing up straight through the middle of that loop. Our dipole moment is pointing straight up, and there's an external magnetic field to the right. Since they're at 90 degrees apart, it's going to torque it according to this, that mu cross B. The magnetic dipole moment is up, the magnetic field is to the right, so the torque is going to make that ring rock. If this is in the J direction and this is in the I direction, it's going to make a rotation in the negative K direction. So one last effect here that we can focus on is the Hall effect. And the Hall effect says that if you have a moving charge in a magnetic field, it will experience a magnetic force perpendicular to the direction of the current flow, because remember, current flow is coming from the drift velocity of those charges. So we've got a battery, it's sending current through a wire, and then it hits this large piece of metal. That large piece of metal is a conductor still, but it's got a width and a thickness to it. The charge is going to drift through that piece of metal, expose them to an external magnetic field. What you see is that you get a voltage that's set up along these outer two locations. Because if you do your right-hand rule for the flow of positive charge, you get positive charges that pile up at the top of the plate, and you get negative charges that pile up at the bottom of the plate. And then the current goes right through the resistor, gives off heat, and the cycle continues. But since we've always said that current really is the flow of negative charges in the opposite direction, you can see that over here on the right side, I've got a negative charge drifting through that piece of metal. And the only thing that would be different if I would hook up a voltmeter is that I would read up a negative potential, which would show me that electrons are truly drifting through the wire. So this is one way. Another way we proved that electrons are the things that are moving. And that voltage, if it was positive, means that positive charges are flowing. If you hook it up and you read a negative voltage, that means that actually electrons are flowing. So the magnetic force must be up, and what happens if you get charges piling up on the top and bottom of this plate right here and here, that means you set up an electric field, and the electric field points from the high to the low voltage. So there's a magnetic force up on the drifting charges, and there's an electric force down. So it looks an awful lot like the velocity selector again, where eventually the charges are equaled out in forces and they just drift through that piece of metal. The question would be, how can we measure this Hall voltage? How can we measure the induced potential between those two plates when they drift through the magnetic field? So if we want to measure the voltage, well, we know that voltage is electric field times the distance of separation. To find our potential difference, I need to know how strong the electric field is. But we can kind of use our ideas, what we said from the velocity selector, and say that, okay, we have a magnetic force up based on V cross B, and what that does is set up an electric field with positive charges at the top and negative charges at the bottom. So there's an electric force down, and this will happen, and these charges will separate until those two forces are equal. So we can actually solve for the electric field by setting the electric force equal to the magnetic force, which we've seen before is QE equals QVB. So I could get rid of the Q again and solve for my electric field to put into my potential equation. So my voltage then would become this. It would be drift velocity times magnetic field times the distance of separation. And the distance of separation here would just be the width of my piece of metal. If we wanted to write this in terms of the current that we knew, well, we have drift speed. We have to remember what current is. Current is NQV times the area, the number of charges per volume, times the area of the wire, times the drift speed, times the amount of charge. I have drift speed. Let's sub in what drift speed is into our voltage equation. So my Hall voltage would be the current over N area times Q multiplied by B multiplied by the width. Now, the area of this metal slab to flow through would be the width of the slab times how thick the slab actually is in three-dimensional space. Because remember, the charges are going to flow through that as a wire. The width times the thickness of the wire here will be how we calculate that area. So really, I could eliminate the width and be left with this, that the Hall voltage is the current multiplied by the magnetic field strength over the number of charges per unit volume times the charge of one electron multiplied by the T, which is the thickness of that piece of metal. The whole point of knowing the Hall voltage is actually to solve for unknown magnetic fields. So if you have this piece of metal in an unknown magnetic field and you run current through it, things that are easily measured for you is the Hall voltage, so the potential that sets up at the edges of the plates. You can measure the current just by using Ohm's law or an ammeter. The number of charges per unit volume is a given depending on what material you're using. The thickness of the wire is completely known because you can measure how thick that piece of metal is, and Q is the charge of one electron. So the only unknown here is the magnetic field strength. So that's the point of measuring out a Hall voltage. So this should help you solve for any of the problems you have left to do in the homework here. The Hall effect plus the torques on current carrying wires. Remember, the current carrying wires create these dipole magnetic moments due to the number of turns, the current, and the area. And if you cross that dipole moment with a magnetic field, we create torques. And those torques will cause the magnetic field loops to rotate. And right now, it looks like it can only rotate from 0 to 180 and back again. It'd be really nice if we could make that whole loop completely spin, and we'll see that in lab